Hi and welcome to another lesson in the physics video series. Today we're going to be discussing the universal law of gravitation, and this very simply shows the gravitational attraction between two masses separated at a certain distance. Alright, let's get started. The universal law of gravitation is based on the attraction of two bodies separated by a certain distance r between them, and we have Henry Cavendish, who discovered the universal gravitational constant g, showing that two objects have a gravitational attraction that is always proportional to the distance squared between them. The experiment that Henry Cavendish set up was a torsion balance which caused two opposing bodies to attract to each other and to swing into place through the force of gravitational attraction, as we see here. The most important part of Henry Cavendish's work is that he proved the universal gravitational constant capital G as 6.67 times 10 to negative 11 Newton meter squared per kilogram squared. Capital G shows the relationship between two masses and the square of the distance proportionality and acceleration due to gravity. Little g is 9.81 meters per second squared. Now let's take a look at the actual formula. The gravitational force formula is equation 10. We have that letter G, the universal gravitational constant, times the two masses divided by the distance between them squared. And the gravitational field strength is associated with this, and this is little g, which is the force per unit mass, also known as the weight. To most easily describe the universal law of gravitation, we know that Fg equals gm1m2 over r squared, and it has this force to distance relationship of the inverse square. The strength of mutual attraction between two masses is proportional to the inverse square of the distances between them. When you have a proportionality and you want to make that proportionality an equality, you need a universal constant, and that's exactly what Cavendish discovered. Let's discuss the weight of Newton's apple and its distance from the center of the earth. Here we have the apple weighing 1 Newton at the surface of the earth. As far as this y-axis is concerned, it is given as the force of gravity. It does not mean that this apple is higher above the earth. As a matter of fact, the horizontal linear scale is the distance above the earth, but the intensity or the strength of the force of gravity is highest, and that is why it is on the y-axis. So the apple weighs 1 Newton at the surface of the earth, and then as you double the distance away, you now see that the apple weighs a quarter of its original strength. Since the apple at the surface of the earth weighs 1 Newton, each earth radii distance, 1d, 2d, 3d, is moving the apple farther away from the center of the mass of the earth. Masses that are farther apart have a weaker attraction, and that's what this chart really shows you. It's not that the apple has less mass as it moves farther away, but the weight of the apple in relationship to the pull of the earth gets less and less because the pull of the earth gets weaker and weaker. Let's take a look at this variation. If the original expression Fg equals gm1m2 over r squared, let's say we doubled the distance. So the original r will be double the r. gm1m2 over some distance, which is now 2r squared. The 2r is doubled, and you get 4r squared. In the bottom of the original equation, you pull out the 1/4, and so you have 1/4 the original gravitational attraction. What if I triple the distance and move 3 times further away instead? gm1m2 over 3r squared. The 3 squared is 9. R squared is in the original formula, so you pull out the fraction of 1/9. 1/9 gm1m2 over r squared is the same as 1/9 of the original force of gravitational attraction. Now, instead of making masses farther apart and causing a weaker attraction, we can bring them closer. So if we started out somewhere, say around 4d, and we cut that distance in half to 2d, r is 1/2 of the original distance. gm1m2 over 1/2 r squared. This turns out to be the inverse of 1/2 squared. 1/2 squared is a quarter. Invert that is 4. Quadruple. So now you have quadrupled the strength. If you took a third of the distance, gm1m2 over 1/3 r squared, you have the inverse of 1/3 squared. 1/3 squared is 1/9. Invert that is 9. So these are the most common fractions. Let's compare them side by side. If you started at a certain distance away from the center of the planet and you moved twice as far away, you've quartered the gravitational attraction. But if instead you moved closer by half the original distance, you have now quadrupled. So you see these are inverted to each other. If you moved 3 times farther away, you have 1/9 the strength. However, if you move to 1/3 of the original distance, you now have 9 times the original strength. Let's take a look at a chart I made to explain this. Here's the chart variation of gravitational field strength according to distance. We're going to start here in the middle. We're going to make all the masses 1, and we're going to ignore the value of g, just so we could look at the proportionalities. If I have a mass of 1 over a distance of 1, 1 times 1 over 1 squared is 1. So whatever this object weighs, that's what it weighs at this distance r. If I go up or down on my chart, up is half and a third, down is double and triple the original distances. Let's work with larger distances. If I start at the original r distance away, here's the original r distance, but I move it to twice as far away. So you are now r and r away. That's 2r. Double squared, have a quarter of the strength. If I have the original r and I move it out 3r away, 1, 2, 3r, 1 over 3 squared is 1/9 of the original force. So you could see that the farther away I get, the weaker the force will be, 1/9. However, if I start at a distance of r away and I bring the mass closer, I bring it back to half its original distance, then you can see that 1 over 1/2 squared, this is the inverse of 1/2 squared. 1/2 squared is a quarter. Inverse of that is quadruple. And then, of course, what if I started and brought it back to 1/3 of its original distance? Then I have the inverse of 1/3 squared. 1/3 squared is 1/9. Invert that. 9. Closer equals stronger. Farther equals weaker. That is the concept in a nutshell. The main factor that determines gravitational attraction between two masses is the distance between them. Yes, you can change the masses, but in nature, usually the mass is already set and is not changing, so it's only the distance between them that changes. Let's now look at the gravitational field strength calculations. We know that the weight of an object is also equal to the gravitational field strength acting on the object. And if we just look at the expanded version of the formula, F sub g equals mg, and F sub capital G is gm1 m2 over r squared. For convenience, I made a big M and a little m. Big M would be like the Earth, little m would be like the apple. The big M is actually the mass of the accelerating body, and that is the mass that causes the smaller object to come towards it. The Earth attracts the apple, and the apple attracts the Earth, but Earth has so much more mass that it doesn't move because of its inertia, whereas the apple has such little mass that that same force of attraction between it and the Earth causes the apple to fall or to be attracted to the Earth. So for any mass or planet or moon, etc., the capital G, which was found by Cavendish, is going to be used in this equation. Little g equals gm over r squared. Here's the g, 6.67 times 10 to the negative 11. Multiplying that by the mass of the accelerating body and dividing it by the radius of the accelerating body squared, that gives you the gravity on any planet or moon. Now let's apply that to the Earth and our moon. So we know that g of the Earth is equal to universal gravitational constant times the mass of the Earth over the radius of the Earth squared. 6.67 10 to the negative 11 Newton meter squared per kilogram squared. That's g, multiplied by the mass of the Earth. This value is on the front page of the reference table, divided by the radius of the accelerating body, which is the Earth. When you divide this into this, you get 9.81 meters per second squared. That's where it comes from. As far as the moon is concerned, it's the same exact formula. G times the mass of the moon divided by the radius of the moon, also on the front page of the reference table. Don't forget to square it, and you get 1.61 meters per second squared. So the rate at which an object falls or gains speed is the g. Little g equals 9.81 meters per second squared for the Earth, and little g equals 1.61 meters per second squared on the moon. And what if you were on the sun? It's the same formula. Little g equals capital G m over r squared. The g is 6.67 10 to the negative 11 Newton meter squared per kilogram squared times the mass of the sun divided by the radius of the sun. And that gives you the gravitational acceleration on the sun, 273.4 meters per second squared. And what is the trend that we notice? Is this simple. The larger the mass of the accelerating body, the greater the gravitational acceleration that mass in its gravitational field experiences. Small bodies have small gravitational pull. Large bodies have a large gravitational pull. I hope you enjoyed this video and thank you for watching. I encourage you to take a look at the Bozeman Science link on this. He does a wonderful job in going over some problems and explaining this concept. We'll see you in the next video.